Hi, everyone. So this is a video to watch for lesson 25. So major reminders, test 2 is on December 2nd in class on Zoom. The review for test 2 is on November 30th. Test 3 is on December 9th in class on Zoom. And the review for test 3 is on December 7th in class. Okay. So this lesson, I'm going to start by talking about 4.8 on rank, nullity, and the fundamental metric spaces. Okay, so this is theorem 4.8.1. The row space and column space of a matrix capital A have the same dimension. Okay, so the row space and column space of a matrix A have the same dimension. Definition 1. The common dimension of the row space and column space of a matrix capital A is called the rank of A and is denoted by rank in parentheses A. The dimension of the null space of A is called nullity of A and is denoted by nullity parentheses A. Okay, so that's the definition of those things. Example 1, find the rank and nullity of the matrix capital A here. Okay, so capital A is a 4x6 matrix. I'm going to construct a 4x6 matrix now. Okay, so the matrix A is the matrix -1, and then use the other entries. Okay, so we're going to find the rank and nullity of that matrix A. So the reduced echelon form of that matrix A is this matrix R. So it's 1. So type this in. Okay, so the reduced echelon form of that matrix R, of that matrix A, is its matrix R. Okay, so since R has 2 leading ones, its row and column spaces are 2-dimensional. And the rank of the matrix A is equal to 2. To find the nullity of capital A, we must find the dimension of the solution space of AX equals 0. Okay. So the general solution of AX equals 0 is the following. So just going to that down there if I need it in the future. I have that. Okay. So we have our solution vector x1, x2, x3, x4, x5, and x6. So this is equal to r times 4, 2, 1, 0, 0, 0 plus s times 28, 12, 0, 0, 1, 0, 0 plus t times 37, 16, 0, 0, 1, 0 plus u times matrix -13, -5, 0, 0, 0, 1. So that's the general solution of AX equals 0. So because the 4 vectors above form a basis for the solution space of AX equals 0, the nullity of A, the dimension of the solution space, is equal to 4. So these 4 definitely span the solution space because you can express the solution space as linear combinations of those 4 vectors. So those 4 vectors span the solution space. They're also linearly independent. So you can see that this is a 1 here, this is a 1 here, this is a 1 here, and this is a 1 here. So none of them can be written as linear combinations of the other 3. They're linearly independent. They span the solution space. So together, those 4 vectors form a basis for the solution space. There are 4 of them. And so we know the dimension of the solution space is 4. A solution space of X equals 0 is 4. That means the nullity of the matrix A is 4. Note, let A be an M by N matrix. Rank of A is less or equal to the min of M and N. Okay, so next is theorem 4.8.2 is the dimension theorem for matrices. So if capital A is a matrix with n columns, then the rank of A plus the nullity of A is equal to n. So if A is a matrix with n columns, then the rank of A plus the nullity of A is equal to n. Okay, so example 3 in example 1. Where we found the rank and nullity of A, where we found, so in this example, we found the rank nullity, right? So in example 1, the rank of A we found is equal to 2. The nullity of A we found was equal to 4. And n, which is the number of columns, Well, the number of columns of A is 1, 2, 3, 4, 5, 6. There's 6 columns, so n equals 6. So if you take the rank, which is 2, and you add the nullity of A, which is 4, 2 plus 4 is 6, which is n. So rank of A plus nullity of A equals n in this example, in example 1. Okay, so that applies to the example we just did. Theorem 4.8.3, if capital A is an M by N matrix, then the following: part A, the rank of your matrix A is equal to the number of leading variables in the general solution of AX equals 0. Okay, so the rank of A is equal to the number of leading variables in the general solution of AX equals 0. And B, the nullity of A is equal to the number of parameters in the general solution of AX equals 0. Okay, so the leading variables in a general solution of AX equals 0 corresponds with the number of leading ones in the reduced row echelon form or row echelon form of A. And then the number of parameters in the general solution of AX equals 0 corresponds with the columns. When you get A to row echelon form or reduced row echelon form, it corresponds to the columns that don't have leading ones in them. And so if you add the number of columns with leading ones to the number of columns without leading ones, you get the total number of columns. Rank of A plus nullity of A is equal to the number of columns of A. Okay. Okay. So next is theorem 4.8.4. If AX equals B is a consistent linear system of M equations in n unknowns, and if capital A has rank R, then the general solution of the system contains n minus R parameters. Okay, so AX equals B, consistent linear system with M equations and unknowns. So there are n unknowns. If A has rank R, then you have R leading variables. And so if you have R leading variables and there are n unknowns, you have n minus R free variables, which correspond with n minus R parameters. Okay, there are 6 important vector spaces associated with a matrix capital A and matrix capital A transpose, A transpose. Okay, so these are the row space of A, 2, the column space of A, 3, the null space of A, 4. Okay, so ignore the spell check, these are mathematical words. 4, row space of A transpose. 5, column space of A transpose. And 6, the null space of A transpose. Okay, so if you have the row space, column space, and null space of A, and the row space, column space, and null space of A transpose. So those 6 are 6 important vector spaces associated with A and A transpose. Okay, so the so the fundamental spaces of a matrix capital A are 1, 2, 3, and 6. Okay, so the row space of A, column space of A, null space of A, and null space of A transpose, those are the four fundamental spaces of a matrix A. Okay. Okay, so theorem 4.8.5. If capital A is any matrix, then the rank of A is equal to the rank of A transpose. Okay. Also, if you have the rank of A and you add the nullity of A transpose, it's equal to M, little m, where it's the number of rows of A. So A is still an M by N matrix. Okay, A is an M by N matrix. Okay, so M is the number of rows of A. So rank of A plus nullity of A transpose is equal to M. Also, if you take the dimension of the row space, which I'm going to write row of A to mean row space of A, it's equal to R. If you take the dimension of the null of A, the null space of A, it's equal to N minus R. You take the dimension of the column space of A, which I'm abbreviating as column A, is equal to R. And if you take the dimension of the null space or null of A transpose, it's equal to M minus R. Okay, so we have these 5 additional equations. So these 4 more after that one. Sure. Good. Okay, so those are more equations about the dimensions of those spaces. Okay, definition. If W is a subspace of N space, Rn, then the set of all vectors in N space Rn that are orthogonal to every vector in capital W is called the orthogonal complement of W and is denoted by W perp. W with a perpendicular sign is a superscript. That's the orthogonal complement of W. The space of all vectors orthogonal to every vector in W. So theorem 4.8.6. If W is a subspace of Rn, then A, W perp, the orthogonal complement of W, is a subspace of Rn. B, the only vector common to W and W perp is 0. So the only place where a vector space W and its orthogonal complement meet is at the single point 0. The orthogonal complement of W perp is W. So if you take the orthogonal complement of W, you get W perp. If you take the orthogonal complement of W perp, the orthogonal complements of the orthogonal complement of W, you get back W. Okay. B, right? So B is saying that if you take W intersected with W perp, you get the 0 set. Second thing, only 0. C is saying that if you take W perp, and then you take perp of that equals W. Okay, so in symbols, that's a short way to say those two things. So quickly, I'm going to the whiteboard. So if you have a space, so if you have R2 and you have a line through the origin. So a line through the origin, remember, is a vector subspace of R2. So W there is a vector subspace of R2. You can talk about its orthogonal complement. Its orthogonal complement is a line perpendicular to that line that goes through the origin. So this is W perp. Okay, all the points on this blue line represent vectors that are orthogonal to every vector in W. So that blue line is W perp. You have the x-axis, y-axis, z-axis, and you're living in R3. Okay, so these are all meeting at the origin. If you have a plane, so if your space W is a plane that goes through the origin, that contains the origin. So you have and it's a plane, so it goes out in all directions. If you have a line, we're in R3, so you have a two-dimensional plane, and its orthogonal complement, W perp, is one-dimensional. 2 plus 1 is 3, right? If you have a line in 2 space, W perp is also one-dimensional. 1 plus 1 is 2. You have to keep in mind the space that you're living in. Here we're living in R3 on the right. Here we're living in R2 on the left. Okay, so that's W perp there. Every point on the line W perp represents a vector that's orthogonal to every vector in W. Okay, so if you have a vector in W, let's say this vector, and you have a vector in W perp, let's say this vector, they're perpendicular to each other. Okay, if you take the same vector in W perp, if you take a different vector in W, it's still perpendicular to that same vector in W perp. Every vector in W perp is perpendicular to every single vector in W. Okay, so let's go back here. So this is theorem 4.8.7. If capital A is an m by n matrix, then A, the null space of A, and the row space of A are orthogonal complements in n space. So the null space of A and the row space of A are orthogonal complements in n space. The null space of A transpose and the column space of A are orthogonal complements in Rm. Okay, so remember A is an m by n matrix. M is the number of rows of A. So the null space of A transpose and the column space of A are orthogonal complements in Rm. Part B of that theorem. Theorem 4.8.8. Equivalent statements. Okay, so we have an equivalent statements theorem already, right? It says a bunch of things are equivalent. And so if A is an n by n matrix, then the following are equivalent, meaning have the same truth value. Capital A is invertible. Okay, this is a continuation of the previous equivalence theorem. So part A is that capital A is invertible. B, AX equals 0 as only the trivial solution. Part C, the reduced row echelon form of A is the n by n identity matrix I sub n. D, A is part D, A is expressible as a product of elementary matrices. Part E, AX equals B is consistent for every n by 1 matrix little b. F. AX equals B has exactly one solution for every n by 1 matrix B. G, determinant of A determinant of A is not equal to 0. H, the column vectors of A are linearly independent. I, the row vectors of A are linearly independent. J, the column vectors of A span Rn. K, the row vectors of A span Rn. L, the column vectors of A form a basis for Rn. J, the column vectors of A, JK, L, JKL, this is M. The row vectors of A form a basis for Rn. N, A has rank N. O, A has nullity 0. P, the orthogonal complement of the null space of A is Rn. Q, the orthogonal complement of the row space of A is the singleton set 0. It's a 0 set. Okay, so all of these statements are equivalent by equivalence statements theorem, A through Q. Okay, so that's the last theorem of that section. So the next section is section 4.9, which is on basic matrix transformations in R2 and R3. Okay. Okay, so for this, we're going to look at the whiteboard for pictures. Okay, so let's go to the whiteboard. Okay, so this is 4.9. Okay, and so this is table 1. Okay, so table is going to have a few columns. First column is going to be an operator. Next column is going to be an illustration. Next column is going to be images of E1 and E2. Right, E1, E2. And the last column is going to be a standard matrix. Just going to stretch this out. It's going to okay. Okay, so the first operator is a reflection about the x-axis. So it's given by t of x comma y, which is equal to x comma negative y. Okay, so the operator is a reflection about the x-axis. So you have an x-axis, you have y-axis, you have a point x comma y, and so vector x is a vector from the origin to that point. And so a reflection about the x-axis would take that vector x and x comma y and map it to x comma negative y. That's a reflection. And so this vector is called t of x. T of x is the reflection of the vector x about the x-axis. Okay, so the images of E1, E2. So t of E1 is equal to t of 1 comma 0, which is 1 comma 0. And t of E2 is equal to t of 0 comma 1, which a reflection about the x-axis is 0 comma negative 1. Okay, so then the standard matrix, the first column is 1, 0, and the other column is 0, negative 1. So what's happening here is that t of E1 is 1 comma 0. So that's the first column of the standard matrix. T of E2, the image of the second standard unit vector E2, T of E2 is equal to 0 comma negative 1, and that's the second column of the standard matrix. So we're getting the columns of our standard matrix from the images under T of E1 and E2. The next operator is a reflection about the y-axis. Okay, so the next one is reflection about the y-axis. Okay, and so the rule for this, or the function, is t of x comma y, which is equal to negative x comma y. Okay, so it's a reflection about the y-axis. It negates the first component, the x component, keeps the y component the same. So if you have your x-axis and y-axis, and you have vector x represented by the point x comma y, and you're reflected about the y-axis, then its new coordinates are negative x comma y. So that's the new vector t of x. Okay, so t of x is negative x comma y. And so the images of E1 and E2 are, well, if you take t of E1, it's equal to t of 1 comma 0, which is negative 1 comma 0. Okay, that's a 0. Okay, and then t of E2 is equal to t of 0 comma 1, which stays the same, 0 comma 1 when you reflect it about the y-axis. And so the standard matrix you get from the images under t of the standard unit vectors. So t of E1 is negative 1, 0. And so negative 1, 0 is the first column of your standard matrix. And then t of E2 is now the second. And so that's the second column. And so you get 0, 1. And so that's the second column of your standard matrix. Okay. So that's a reflection about the y-axis. And then the third one is reflection about line y equals x. Okay, and that's given by the rule or function t of x comma y is equal to y comma x. It just switches the coordinates of a point. It represents a reflection about the line y equals x. Okay, so if you have your x-axis and y-axis, and you have a vector x represented by the point x comma y, and then you have the line y equals x. And you reflect the vector x comma y, and you get the vector y comma x. You get the vector y comma x. Okay, so then that vector is t of x. That vector is t of x. It's the result of reflecting a vector x about the line y equals x. And you just switch the coordinates of the point. So t of E1, t of 1 comma 0 is 0 comma 1. T of E2, t of 0 comma 1 is 1 comma 0. You just switch the point, switch the coordinates. And then the standard matrix is 0, 1 for the first column and 1, 0 for the second column. And then that's the standard matrix for that. Okay? And so those are the first three operators, table 1. These are basic matrix transformations in R2, R3. Left multiplying a vector by these matrices gives you the resulting vector under T. Okay, so just to quickly explain what I mean by that. So example, so the standard matrix for reflection about the line about the x-axis from the whiteboard is this matrix. Okay, so we found the standard matrix is this. Okay, that's a standard matrix for reflection about the x-axis. So we can use this matrix to get the result of reflecting a vector in R2 space about the x-axis. Okay, so let's say you have the vector. Let's say you have the vector 3, 2, and you want to reflect it about the x-axis, and you just left multiply it by the standard matrix. Okay, if you left multiply it by the standard matrix, the result, you have a 2 by 1, 2 by 2 times 2 by 1, it's a 2 by 1 matrix. So if you multiply this, you get 3, negative 2, which is the result of reflecting 3, 2 about the x-axis. Reflecting a vector about the x-axis means you negate its y component. So if you take the vector 3, 2 and reflect it about the x-axis, you negate its y component and you get 3, negative 2. So instead of negating the y component, you can left multiply it by the standard matrix for the matrix transformation of reflection about the x-axis. Okay, so you can use the standard matrix to left multiply vectors to get the resulting vector after the transformation. Okay, and so these tables I'm going to be making is finding these standard matrices that represent these transformations. Okay, so in table 2, we have now more categories here. I'll give myself more space this time to work with. Improve upon my method here. Okay, so we have the operator. We have the illustration. The images of E1, E2, and E3. Now we have the standard matrix. Okay, so first let's have a reflection about the xy plane represented by d of x comma y, which is equal to x comma y comma negative z, x comma y comma z, d of x comma y comma z equals x comma y comma negative z. Okay, so reflection about the xy plane. So now we're in 3 space. So we have the x-axis, okay, so we have the x-axis, y-axis, and z-axis. Okay, here's the xy plane going in all directions. We have, let's say, a vector x with coordinates x, y, z. And if we reflect it about the xy plane, we get a vector x, y, negative z. You just negate the z component. Okay, that's the effect of it. So if you have a vector x, then t of x is negating the z component. So t of E1, remember E1 in R3 is 1, 0, 0. E2 in R3 is 0, 1, 0. And E3 in R3 is 0, 0, 1. Okay, so T of E1 is just negating the Z component, which doesn't change it. T of E2 is negating the Z component, which doesn't change it. Then T of E3 is negating the Z component, which does change it, and now it's 0, 0, negative 1. So those are the images under T of the 3 standard unit vectors for R3. And then the standard matrix is built from the images under T of E1, E2, and E3. So the first column is the image under T of E1, the second column which is the image under T of E2, and the third column is the image under T of E3. So, right, so this is the first image. This is T of E1. This is T of E2. And this is T of E3. Those are the 3 columns in that order that form the standard matrix. Okay, the next operator is a reflection about the XZ plane. And that's represented by T of X, Y, Z is equal to X comma negative Y comma Z. It's a reflection about the XZ plane. Okay, so if you have your x-axis, your y-axis, your z-axis, and you have the xz plane, which is now this direction, going in all directions there. And if you have a vector x, so if you have a vector x, which is x, y, z coordinates, that's vector x, and you reflect it about the xz plane, the effect of that reflection is just negating the y component. So you have x comma negative y comma z. That's the vector t of x. Okay, so you're just reflecting that point throughout the xz plane. And so t of E1 just negating the y component doesn't change the vector. T of E2, negating the y component does change the vector. And T of E3 doesn't change the vector either. And you get 0, 0, 1. Okay. And so the standard matrix is built from those images. You have 1, 0, 0, 0, negative 1, 0, 0, 0, 1. So now that's the standard matrix for reflection about the XZ plane. And then the third operator in table 2 is orthogonal projection onto, oh no, sorry. It's a reflection about the YZ plane. And then it's T of X comma Y comma Z is equal to negative X comma Y comma Z. Okay. Good. Okay, so you have the x-axis, you have y-axis, you have z-axis. And so now you have reflection about the YZ plane. So the YZ plane is over here. Okay. There's the YZ plane. And so if you have a vector x, whose coordinates are x, y, z, and you reflect about the x, z plane, you want to negate its x component. So if you negate its x component, it's a matter of perspective. It's going further into the board in my picture. So you're just negating the x component. So it's x and then t of x back. So if the vector was in front, let's say the YZ plane was a vertical wall and you're in front of the wall in the vector x, t of x would then be behind it because you'd be negating the x component, x going in or out of the board. Okay, of the wall. Okay, so now, so you're negating the x component when you reflect about the YZ plane. So T of E1 is negating the x component, which changes the vector negative 1, 0, 0. T of E2 negates the x component, but doesn't change the vector because the x component is 0. And then T of E3 is equal to 0, 0, 1. Okay, so now you have the images under T of E1, E2, and E3. So E1, T of E1 is the first column, T of E2 is the second column, and T of E3 is the third column. Just writing 0. Okay, so that's the standard matrix for reflection about the YZ plane. So if you take a 3-tuple and left multiply it by this matrix, the effect is the reflection about the YZ plane of that 3-tuple. It's negating the x component. Okay, so that's table 2. Okay, table 3. Okay, so for table 3, so you have an operator. You have an illustration of that operator. You have images under this T of E1 and E2. And you have a standard matrix. Okay. So the first operator is the orthogonal projection onto the x-axis. Okay, and so it's T of x comma y is equal to x comma 0. So orthogonal projection onto the x-axis. So if you have your x-axis and you have your y-axis, then if you have a vector x with coordinates x comma y, then the orthogonal projection is just going to be this vector, which is coordinates x comma 0. You just make the y component 0. Okay, so that's t of x. Okay, so the images under E1, E2, E1, E2 are now in R2. So E1 is 1, 0, E2 is 0, 1. So T of E1 is just 1, 0. And T of E2 is 0, 0. Because 0, 1 make the second component 0, 0, 0. So the standard matrix is now the first column is 1, 0, the second column is 0, 0. That's the standard matrix for that operation. Okay, so the next one is the orthogonal projection onto the y-axis. So if you have t of x comma y, it's equal to 0 comma y. Okay, so you just put a 0 for the x component. So you're just projecting the vector onto the y-axis. So you have the x-axis, y-axis. You have a vector x comma y projected onto the y-axis, and you get the vector 0 comma y. Okay, so this is the vector t of x. The original vector was x. And so t of E1 is 0, 0. T of E2 is 0, 1. So the standard matrix, first column is 0, 0. The second column is 0, 1. And that's the standard matrix for the orthogonal projection onto the y-axis. Okay, so that's table 3. Table 4. So for table 4, we have an operator. Illustration. Images of E1, E2, E3. We have a standard matrix. Okay, so the operator here is the orthogonal projection onto the xy plane. And it's t of x comma y comma z is equal to x comma y comma 0. She's just making the z component 0. So as an illustration, you have the x-axis, you have the y-axis, and you have the z-axis. And so if you have a vector x with components x, y, z, you just want to make the z component 0. So you just want to make its height 0. So you're like projecting this point onto the xy plane because you're making its z component 0. So this is x comma y comma 0. Okay, so that's t of x. X is representing the entire vector, 3-component vector. Okay, so t of E1, E2, E3 are in R3. T of E1 is making the z component 0, so it stays the same. T of E2 makes the z component 0, stays the same. But T of E3 is making the z component 0. So 0, 0, 0. Okay, and so that's the standard matrix there. Okay, and then and so next one is the orthogonal projection onto the xz plane. So you have t of x comma y comma z is equal to x comma 0 comma z. So if you project it onto the xz plane, that means you make the y coordinate 0. Okay, so if you again have the x-axis, y-axis, and z-axis, then you have a vector x comma y comma z. Then when you project it onto the xz plane, you're just removing the y component. So if you remove the y components, you're projecting it onto the xz plane. And so you get a vector in with y component 0. So this is x comma 0 comma z. This is t of x. Okay, so the y component is now 0. So t of E1 is making the y component 0, which is already was, so it stays the same. T of E2, you make the y component 0, and now you get the 0 vector, it changes that vector. And t of E3 stays the same because the y component was already 0. And so that's the images under T of E1, E2, and E3, and they make up the columns of the standard matrix. And so now you get this. This is the standard matrix for the orthogonal projection onto the xz plane. And now the third one in table 3 is the orthogonal projection onto the yz plane. Okay, and that's represented by T of x comma y comma z is equal to 0 comma y comma z. Okay, and so for this one, you project it onto the yz plane. So you make the x component 0. So if you have the x-axis, y-axis, and z-axis, and you have a vector x, y, z, and you want to make projected onto the yz plane, then you just want to make the x component 0. So to make the x component 0, I'm just going to draw this vector a little bit further out. It'll be like this. So you have x, y, z. We're going to project that vector x onto the yz plane. So if you project it onto the yz plane, you get something like this. Get a vector here. This is t of x. And its coordinates are 0, comma y, comma z. You're just making the x component, the first component, 0. Okay, so t of E1, if you make the x component 0, it becomes a 0 vector. T of E2, E2 is unaffected, so it stays 0, 1, 0, because the x component was already 0. And then T of E3 is equal to 0, 0, 1. And so those are the images under T of those 3 vectors. So you have 0, 0, 0, 0, 1, 0, 0, 0, 1. So those are the 3 columns that form the standard matrix for the orthogonal projection onto the xz plane, onto the yz plane. Okay, so you have those 3 corresponding standard matrices. Okay, so now you have table 5, which is these operations. So you have your operator, illustration, rotation equations, and standard matrix. So the operator is a counterclockwise rotation about the origin through an angle theta. I'm gonna write the symbol for theta instead of the word theta. Through an angle theta. Okay, so counterclockwise, that's counterclockwise, the E at the end. Counterclockwise rotation about the origin through an angle of theta. Okay, that's our operator. So the illustration of that is the following. So we're going to be living in two space here. So you have an x-axis, you have a y-axis, and if you have a vector x comma y, coordinate vector x with coordinates x comma y, and you rotate it about the origin through an angle of theta, then the effect is just, imagine the tip of that vector on a circle, and you're just moving along that circle with the radius, the magnitude of that vector. And you end up at another vector called w, which is the effect of this transformation with components w1 comma w2. And the angle of that rotation is theta. And it's theta in the counterclockwise direction. This is angle theta in the counterclockwise direction. Okay, so that's an illustration of counterclockwise rotation about the origin through an angle of theta vector. So the rotation equations are w1. The first component of the resulting vector is equal to x cosine theta minus y sine theta. Sine. And then w2 is equal to x sine theta plus y cosine theta. Okay, and so the standard matrix there is just cosine theta minus sine theta and sine theta cosine theta. If you take the vector x, y, and left multiplied by this, you end up with components w1 and w2 like that. Okay. Okay. So right. So how do you get these two column vectors? So you have this column and you have this column. So if you rotate E1, if you rotate counterclockwise E1 about an angle of theta, the effect is the vector cosine theta comma sine theta. Okay. So that's the first column. And then if you take E2, take the image under T of E2, if you counterclockwise rotate E2 through an angle, if you counterclockwise rotate the vector E2 about the origin through an angle of theta, you get sine theta, comma cosine theta. And this is a negative here, or negative sine. It's negative sine theta. Okay, And so then that's how you get the two columns of the standard matrix. So the images under T of E1, E2, just as before. If you have the XY axis, this is just illustrating the images under T of E1 and E2. You have the unit, the radius 1 circle. Okay, this is radius 1. And if you E1 is this vector, okay, that's E1. And if you rotate it, about an angle of theta counterclockwise, you get T of E1, whose components are cosine theta, comma negative sine theta.
Oh, okay. Yeah.
Oh. This is cosine theta, negative sine theta. Sine theta, cosine, that's it. Okay, so then, okay, fix that. Okay, so see the new standard matrix. Okay, so T of E1 is cosine theta, comma sine theta, what I originally wrote here. Okay, and then this is negative sine theta, comma cosine theta. Okay, so T of E1 is the effect of rotating E1 about an angle of theta counterclockwise, right? So while E1 is the vector 1, comma 0, T of E1 is cosine theta, comma sine theta. Okay. And similarly for E2, you rotate counterclockwise by theta of E2, you get T of E2, which is negative sine theta, comma cosine theta. Okay. All right, so that's table 5. We're almost done with tables. So, so this one is orthogonal projections onto lines through the origin. Okay, so if you have the x-axis, and you have the y-axis, and you have a line L through the origin, goes through the origin. So you have a line L here. And if you have a vector x, then you just project it onto that line. Get a vector here along that line. And so this is T of x. Just projected that vector onto that line. Okay, and so the standard matrix for this is called P sub theta, where theta is the angle that that line makes with the x-axis in the counterclockwise direction. So positive, it's that way, negative would be below the x-axis. So P sub theta, the standard matrix for P sub theta, orthogonal projection onto a line L through the origin, is equal to, in terms of that angle theta of that line, is cosine squared theta 1/2 sine of 2 theta for the first column, And then the second column is 1/2 sine of 2 theta again. 2 theta. And then sine squared theta. Okay, so that's the standard matrix with that operation. Okay, and so with that, we are done with 4.9. Okay, and so the next one is 4.10, which is on properties of matrix transformations. Okay, so if we have T sub B composed with T sub A of X, it's equal to T sub B of T sub A of X. Okay, so this is equation 1 in this section. So if we take T sub B composed with T sub A of X, where their matrix T sub A and T sub B are matrix transformations, this is T sub B of T sub A of X. And so T sub B is left multiplication by the matrix B. So this is B times T sub A of X. And T sub A of X is left multiplication by A. And so it's AB X. Wait, so it's BA. B times AX, which is equal to BA X. Okay, so T sub A of X is left multiplication by A. T sub B is left multiplication by B. T sub A of X is AX, and then B times AX is BA times X. Okay, so what this is saying is that T sub B composed with T sub A is equal to T sub BA. The effect of T sub B composed of T sub A of X is equal to left multiplication by the matrix BA. So you can think of, instead of left multiplication by A, then left multiplication by B, you can think of a single left multiplication by BA. Okay, so that's what that equation is saying. So this is equation 2. Okay, and so if you have T sub C composed with T sub B composed with T sub A, it's equal to T sub CBA. Okay, left multiplication by A, then B, then C is the same as a single left multiplication by CBA. And this is equation 3. Okay, so note, we will denote the standard matrix for transformation T from Rn to Rm by a single bracket T. Thus, T of X is equal to bracket T X, left multiplication by the matrix, standard matrix for T, bracket T. So the standard matrix for T2 composed with T1 is equal to the standard matrix for T2 times the standard matrix for T1. Okay, and so this is equation 4, and this is 2 restated. Okay, so equation 2 is just another way of writing it. And the standard matrix for, and the standard matrix for T3 composed with T2 composed with T1 is equal to the standard matrix for T3 times the standard matrix for T2 times the standard matrix for T1. This is equation 5. And this is 3 restated. Okay, so a fact. T2, the standard matrix for T2 composed with T1 is not equal to the standard matrix for T1 composed with T2. So if you switch the order, the standard matrices don't have to be the same. It's false in general. Sometimes it can be true, but in general it is not. Okay, fact. Composition of rotations is commutative. So that means that if you have 2 rotations, it doesn't matter the order of those rotations. So that means if you have 2 rotations, the order of them does not matter. If you rotate by 30 degrees and 60, you can rotate by 60 then 30, and it doesn't matter if you change the order. Okay, so the operator T of x, which is equal to negative x on R2 or R3, is called the reflection about the origin. Okay, and so the standard matrix for a reflection about the origin on R2 when living in R2 is -1, 0, 0, -1. This is on R2. Okay, so if you take, so negating a vector is the effect is reflecting about the origin. And so if you take the vector left multiplied by this matrix, you get the reflection of it about the origin in R2. Definition. Okay, a matrix transformation. T sub A from Rn to Rm is 1-to-1 if T sub A maps distinct vectors or points in Rn into distinct vectors in Rm. Okay, so a matrix transformation is 1-to-1 if it maps distinct vectors in Rn into distinct vectors in Rm, meaning it can't map 2 different vectors to the same vector. That would be a 1-to-1 matrix transformation. Rotation operators on R2 are 1-to-1 since distinct vectors that are rotated through the same angle have distinct images. So if you take 2 different vectors and rotate them, both of them by the same amount, the effect is still 2 different vectors. So that is a 1-to-1 matrix transformation. Okay, and orthogonal projection of R2 onto the x-axis is not 1-to-1 because it maps distinct points on the same vertical line into the same point. All you have to do is think of multiple points on the same vertical line. If you project all of them onto the x-axis, all these distinct points on the same vertical line will then be projected onto the same point on the x-axis. And so the matrix transformation of taking points and then taking the orthogonal projection onto the x-axis is not a one-to-one matrix transformation. It takes different vectors and maps them to the same vector. And so that transformation is not one-to-one. Okay, definition 2. If T sub A from Rn to Rm is a matrix transformation, then the set of all vectors in Rn at T sub A maps into 0 is called the kernel of T sub A and is denoted by ker of T sub A, by that kernel of T sub A. The set of all vectors in Rm that are images under this transformation of at least one vector in Rn is called the range of T sub A. And is denoted by capital R of T sub A. Okay, so the kernel of T sub A is equal to the null space of A. The range of T sub A is equal to the column space of A. Okay, so this is equation 6 in this section. This is equation 7 in this section. Theorem 4.10.1. If A is n by n matrix, and T sub A is from Rn to Rn, is the corresponding matrix operator, then the following are equivalents. A, capital A is invertible. B, the kernel of T sub A is the 0 set. So the only thing that T sub A maps to 0 is 0. C, the range of T sub A is Rn. And D, T sub A is 1-to-1. Okay, that's short for 1-to-1. So 1, 2, 1, and I'm abbreviating it at that 1-1. Okay, so if A is n by n, T sub A from Rn to Rn is the corresponding matrix operator. The following are equivalent. These four statements have the same truth value. They're all true or they're all false. Example 5. Prove the rotation operator on R2 is 1-to-1. Okay, so the standard matrix for the rotation operator on R2 was given by, you have cosine theta here, you have negative sine theta, you have sine theta, you have cosine theta. Okay, if you take the determinant of that matrix, you get cosine squared theta plus sine squared theta. And that's a trig identity equals 1. And 1 does not equal 0. So the determinant of t does not equal 0. Therefore, t is invertible by the equivalence theorem, by theorem 2.3.8. Okay, and so therefore, the standard matrix for t is invertible by theorem 4.10.1, parts A and B. Okay, so part A of this theorem says that the matrix is invertible, and part D says T sub A is 1 to 1. Okay, so T is invertible. So since T is invertible, T sub A is 1 to 1. So here is T sub A is 1 to 1 by that theorem. Okay, so T sub A is 1 to 1 because T is invertible, and that's equivalent to T sub A being 1 to 1. And so we proved that the rotation operator is 1 to 1 by the equivalence theorem, theorem 2.3.8. That's the equivalence theorem. And let's last theorem, theorem 4.10.1, parts A and part D are equivalent. Okay. So new thought. Okay. If T sub A from Rn to Rn is a 1 to 1 matrix operator, then okay, so that's good. Okay, all right. Okay, good. Okay, so okay, so if you take T sub A, if you take T sub A inverse, the matrix operator for A inverse, you have a map from Rn to Rn. And so that corresponds with A inverse. Is called the inverse operator of T sub A. Okay, so if you take T sub A composed with T sub A inverse, that's equal to T sub A inverse. This is equal to T sub I, the identity matrix I. And this is if and only if T sub A T sub A inverse of X is equal to A inverse of X, which equals to IX, which equals X. Okay, and the opposite direction also applies. So if you have T sub A inverse composed with T sub A, this is equal to T sub A inverse A equals T sub I, if only if T sub A inverse of T sub A of X is equal to A inverse A X, which is equal to IX, which is equal to X. Okay, so now if you do the composition in the other direction, that also applies. And so what this shows is that T sub A inverse is equal to the inverse of T sub A. Okay, or in terms of standard matrices, standard matrix of T inverse is equal to the standard matrix of T, the inverse of that. Okay, so this is equation 8 in this section, and this is equation 9 in this section. Okay, so adding, this is now, this is the equivalence theorem extended. Okay, so we had parts A, B, C, D, E, F, G, H, I, J, K, elemental P, Q. And so R, part R, is that the kernel of T sub A is singleton set 0. S, I'm just going to put R period there. S is the range of T sub A is Rn. And then T is that T sub A is 1 to 1. Okay, so in the last lesson, this same lesson, we had the equivalence theorem. I wrote out all the parts of theorem A through Q. And so I'm extending that to this theorem. So this is theorem 4.8.8. Okay, so we're just extending the theorem 4.8.8. Extension of theorem 4.8.8. Okay. Okay, so now we're adding R, S, and T. So all of those are equivalent. Okay, and so that is the end of chapter 4, and that is the end of material on S2. Okay. So I'm going to talk a little bit about chapter 5. So chapter 5 is on eigenvalues. So this is stuff on the third exam, not on the second one. So this is on eigenvectors, eigenvalues, and eigenvectors, and this is 5.1. So definition. If capital A is an n by n matrix, then a non-zero vector x in Rn is called an eigenvector of A or of T sub A if AX is a scalar multiple of X. That is, AX is equal to lambda X. For some scalar lambda. Okay, so lambda is an eigenvalue of A or a piece of A, and X is said to be an eigenvector corresponding to lambda. Okay, move this down here. Okay, so a non-zero vector X is called an eigenvector of A if AX is a scalar multiple of X. AX equals lambda X for some scalar lambda. Lambda is an eigenvalue. The name of lambda is an eigenvalue of A. X is said to be an eigenvector corresponding to lambda. So if for a vector X, AX equals 3X, 3 would be an eigenvalue, and X, that vector X where that worked, would be an eigenvector corresponding to lambda equals 3. Okay, let me do an example. So example 1. If you have a vector X and it's equal to the 2 by 1 vector 1, 2, is say X is an eigenvector of matrix A, which is a 2 by 2 matrix, 3, 0, 8, -1. And so this is an eigenvector of that matrix corresponding to lambda equals to 3. Since if you have AX, it's equal to, well, that's A, and this is X. If you multiply them, you get the 2 by 1 matrix. Three, 6, and 3, 6 is 3 times the 2 by 1 matrix that we started with, 1, 2. So this is equal to 3x. So AX is equal to 3x. And so that means that this vector X is an eigenvector of A corresponding to lambda equals 3. So there's the lambda equals 3. And this is the 3 here. Okay. This is the vector X. This is the vector X here. Okay, so AX is equal to 3x. The 3 is the eigenvalue. The X is the eigenvector corresponding to lambda equals 3. Okay, so theorem 5.1.1. If capital A is an n by n matrix, then lambda is an eigenvalue of A if and only if it satisfies the equation determinant of lambda I minus A is equal to 0. So this is equation 1 in this section. This is called the characteristic equation of A. So if A is n by n, and then lambda is an eigenvalue of A, if only if it satisfies this equation. And this is called the characteristic equation of a matrix A. Okay, so let's say you have the same matrix A in example 1, this matrix here, right? So A is equal to that. Okay, now let's say we take the determinant of lambda I minus A. That's the determinant of lambda I minus A. Well, if you take lambda I minus A, then the resulting matrix, so maybe I'll write this out for you. If you have lambda I, and you're taking that matrix and you're subtracting A from it. So lambda I, remember lambda is 3. So A is that matrix, and lambda is 3 from that example. Right? So lambda I would be 3 times I. So that'd be 3, 0, 0, 3. That's lambda I. And minus A, which is 3, 0, 8, negative 1. You want the determinant of that. So you have the determinant of the 2 by 2 matrix where you have 3 minus 3, which is 0. You have 0 minus 0, which is 0. 0 minus 8, which is negative 8. And 3 minus negative 1, which is 4. So you get the determinant of I'm sorry, I'm applying it to lambda as 3. It would work. Okay, I'm doing a general one. Okay, so that's lambda. Okay, so lambda, you're solving for all such lambdas. So that you have the determinant. And so you have this. So here you have lambda minus 3. Here you have lambda. So you have 0, because lambda times 0 is 0 minus 0, which is 0. Here you have negative 8. And here you have lambda plus 1. I see the determinant of that matrix. So you're setting equal to 0 because you're solving the equation determinant of lambda I minus A equals 0. So that's the determinant of lambda I minus A and equals 0. And you want to solve that equation. So you take the determinant, or AD minus BC, you get lambda minus 3 times lambda plus 1, which is minus negative 8, is equal to 0. So minus negative 8 is equal to 0. And so when you multiply this, minus 0, sorry, minus 0, because 0 times 8 is 0. So this gives you lambda minus 3 times lambda plus 1. Lambda minus 3 times lambda plus 1 is equal to 0. And so that means the eigenvalues of capital A are lambda equals 3 and lambda equals minus 1. Okay, so here's A. The determinant of lambda I minus A is this determinant of this matrix. You said equal to 0. That's the determinant of lambda I minus A equals 0. It's called the characteristic equation of A. Solve for lambda. So you compute the determinant on the left side, which is lambda minus 3 times lambda plus 1, set equal to 0. The only two values of lambda that make that equation hold are lambda equals 3 and lambda equals minus 1. Lambda is 3 makes the first factor 0. Lambda equals minus 1 makes the second factor 0. Anything else would make neither factor 0. The product of two non-zeros is not 0. Okay, so this is the only 3 solutions to that equation. So those are the only 2 eigenvalues of that matrix A. Okay, so when the determinant of lambda I minus A is expanded in the characteristic equation, which is equation 1 right here. Get the characteristic equation of the matrix A. So what that is, it's lambda to the n plus C1 lambda to the n minus 1 plus C2 times lambda to the n minus 2 plus plus C sub n is equal to 0. This is equation 3. Okay, the polynomial p of x, which is equal to x to the polynomial p of lambda which is equal to this, expression is the characteristic polynomial of A. Okay. This is the characteristic equation of A. This is the characteristic polynomial of A. Okay, so next is theorem 5.1.2. If capital A is an n by n triangular matrix, then the eigenvalues of A are the entries on the main diagonal of A. Okay, so if you have a triangular matrix, then the entries on the main diagonal of A are the eigenvalues of that triangular matrix. It's only for triangular matrices. Theorem 5.1.3. If capital A is n by n, an n by n matrix, then the following are equivalent statements. Then the following are equivalent. Part A, statement A, lambda is an eigenvalue of A. B, lambda is a solution of the determinant of lambda I minus A is equal to 0. C, the system of equations lambda I minus A x equals 0 as non-trivial solutions. D, there is a non-zero vector x such that ax is equal to lambda x. Okay, so if A is an n by n matrix, then the following four statements are equivalent. Lambda is an eigenvalue of A. Lambda is the solution of the determinant of lambda I minus A equals 0. It's an equation. Lambda is the unknown, and so all its solutions has solutions. C, the system of equations lambda I minus A times x equals 0 has non-trivial solutions, meaning you can plug in an x here which is not 0, and that equation holds. There's a non-zero vector x such that ax equals lambda x. Okay, so these are statements made about lambda. So lambda is an eigenvalue of A would be equivalent to the system of equations for that fixed lambda. Lambda I minus A would then be a matrix, and then that matrix times x equals 0 would have non-trivial solutions. And again, here lambda is a fixed value. This lambda here, there's a non-zero vector x such that ax equals lambda x for a fixed lambda. Okay, so those four statements are equivalent for an n by n matrix A. The eigenspace of A is a new thought corresponding to lambda can be viewed as 0. These are four ways to view it. The non-zero vectors that satisfy lambda I minus A times x equals 0. So you can view the eigenspace of A corresponding to lambda as one way. Way 0 is the non-zero vectors that satisfy that equation. B, 1, the null space of lambda I minus A. Okay, so the non-zero vectors that satisfy that space is the null space of lambda I minus A. Okay, so the things that that left multiplication by this gets sent to 0. 2, the kernel of T sub lambda I minus A, same idea. It's a map from R n R n. Another way to express the solutions of this equation is saying that if you have a matrix operator T sub lambda I minus A, which is left multiplication by that matrix, or lambda I minus A times X, the kernel of it would be all vectors X that are set to 0. This is just another way of saying the same thing. And then 3, the set of vectors little x such that AX equals lambda X. And that's original meaning of an eigenvalue and eigenvectors. The eigenspace of A corresponding to lambda is the space of all vectors that are eigenvectors corresponding to lambda. The eigenspace of A corresponding to lambda is the set of all vectors x such that AX equals lambda x for a fixed value lambda. Okay, so each lambda has its own eigenspace. Okay, each lambda has its own set of vectors such that AX equals lambda x. Okay, so in example 6, we find the bases for the eigenspaces of matrix A, which is the matrix, which is this 2 by 2 matrix, -1, 3, 2, 0. Okay, so solution. So we have the determinant of lambda I minus A. It's equal to the determinant of this 2 by 2 matrix, where you have lambda plus 1 here, -3 here, -2 here, and lambda here. Okay, so lambda I minus A is a matrix, given that this is A, is this matrix. Okay, you want the determinant of that? Well, then you do AD minus BC, and you get lambda times lambda plus 1 minus 6, which is equal to, when you get lambda squared plus lambda minus 6, which is lambda minus 2 times lambda minus lambda plus 3. Let's set that equal to 0. Just going to quickly plug in charger. Okay. Okay, good. Okay, so we're finding all the solutions to determinant of lambda I minus A equals 0. And so the eigenvalues of A are lambda equals 2 and lambda is equal to -3. So those are the 2 eigenvalues. Okay. So we have eigenspaces corresponding to each of those eigenvalues. Okay. By definition, x is an eigenvalue of A corresponding to lambda if only if lambda I minus A times x is equal to 0. Or that last statement, that this matrix times x1, x2 is equal to the 2 by 1 zero matrix. Okay, so I'm just rewriting this equation in matrix form. Okay, so x is an eigenvalue of A corresponding to lambda. This vector is an eigenvalue of A corresponding is an eigenvector. Sorry, eigenvector of A corresponding to lambda, if and only if it satisfies this equation for that fixed lambda. So let's first look at lambda equals 2, which is one of the two possible eigenvalues of A. So if lambda, okay, so if lambda is equal to 2, you have this equation. You're plugging in 2, right? And so now you have that equation. But if you plug in lambda equals 2, then you get 3, negative 3, negative 2, 2. You get that equation. Okay, and so it has general solution of x1 is equal to t and x2 is equal to t. So you can find a general solution of this matrix equation and get x1 equals t and x2 is equal to t. Okay, and so what that means is that your vector x1, the solution vectors x1, x2 are of the form t, t, which is equal to t times the vector 1, 1. Okay, and so that means that the vector 1, 1 forms the basis for the eigenspace corresponding to lambda equals 2. Okay, so similarly, you can do the same procedure for lambda equals negative 3, and you can get that negative 3/2 1 is a basis for the eigenspace corresponding to lambda equals negative 3. Okay, so we've now completed the goal of finding bases for the eigenspaces of that matrix. We find the two eigenvalues of it are 2 and negative 3, so they each have eigenspaces corresponding to them. And so we found the basis for the eigenspace corresponding to lambda equals 2, and we found a basis for the eigenspace corresponding to lambda equals negative 3. So theorem 5.1.4, a square matrix, capital A, is invertible if only if lambda equals 0 is not an eigenvalue of A. Okay, and theorem 5.1 0.5 heading to the equivalent statements theorem. Okay, so the equivalent statements theorem up to this point is this. Okay, now we're just going to, since I'm on Word, I can actually add on to it directly. So I'm going to do that. So then So now I'm just adding on to the previous one. So if A is an n by n matrix, the following are equivalent. We stopped at T before, and now X is U. And it's that lambda equals 0 is not an eigenvalue of A. That's another equivalent statement. Okay. And definition 2, if T from V to V is a linear operator on a vector space capital V, then a non-zero vector X in V is called an eigenvector of T. If T of X is a scalar multiple of X, that is, T of X is equal to lambda X for some lambda. Lambda is an eigenvalue of T, and X is an eigenvector corresponding to lambda. Okay, the eigenspace of T corresponding to lambda is the kernel of T sub lambda I minus A, or the space or the subspace of V such that T of X is equal to lambda X. Okay, and so that is the end of 5.1. So you're almost done with this lesson. I just want to talk about 5.2, which is on diagonalization. So okay, so let's say A and P are, so 5.2. Okay, A, P are n by n matrices, and P is invertible. So let's say we have a similarity transformation from A to P inverse AP. Okay, let capital B equal to P inverse AP. Then determinant of B is equal to the determinant of A. Okay, and this is since if you take the determinant of B, it's equal to the determinant of P inverse AP, because they're the same. But this is equal to the product of those determinants. It's equal to the product. It's equal to the product. It's equal to the product determinant of P inverse times determinant of A times determinant of P. And determinant of P inverse is 1 over the determinant of P, still but times determinant of A times determinant of P. But notice that determinant of P divided by determinant of P is 1, so this is equal to determinant of A. So determinant of B equals determinant of A. Okay, so in table 1, these are similarity and variance. Okay, so on this side is the property, and on this side is the description. So the property is determinant, and the description is that A and P inverse AP have the same determinant. Invertibility. Okay. A is invertible if only if P inverse AP is invertible. Okay, rank. A and P inverse AP have the same rank. Nullity. A and P inverse AP have the same nullity. Trace. A and P inverse AP have the same trace. Characteristic polynomial. A and P inverse AP have the same characteristic polynomial. Eigenvalues. We predictable here. A and P inverse AP have the same eigenvalues. Eigenspace dimension. Okay, and this I'll have to say a little more. If lambda is an eigenvalue of A, and hence of P inverse AP, then continuing, then the eigenspace of A corresponding to lambda and the eigenspace of P inverse AP corresponding to lambda have the same dimension. Okay, so when you take a transformation from A to P inverse AP, the effect is that a lot of these things stay the same. Okay, almost done with the lesson. Definition 1: if A, B are square matrices, then B is similar to A if there is an invertible P such that B is equal to P inverse AP. Okay. Okay, so B similar to A implies that A is similar to B. So we say A and B are similar instead of one is similar to the other. Definition 2. Okay, a square matrix capital A is diagonalizable if it is similar to some diagonal matrix capital P. P diagonalizes A. Okay. Theorem 5.2.1, if A is n by n, the following are equivalent. A, that A is diagonalizable, and B, A has n linearly independent eigenvectors. Okay. Okay, so we're going to stop here. Okay. So next class, we will continue. The homework for after Thanksgiving does not have any chapter 5 in it. The homework is the same as I wrote down at the end of lesson 24. So at the end of lesson 24, I gave you this homework. So it's the same. Okay. So assuming you got to this point, you've watched the video. So, okay, so that was covered. Now the line goes away. Okay. So this is still, it's the same homework I posted at the end of the last lesson. It's now you've watched this video, and so now you're prepared to do these extra sections, okay? So this is the only homework. There's no homework yet on chapter 5. I am going to assign homework that I covered in 5.1 and 5.2 next class, okay? But it will be due, the chapter 5 homework would due after the exam 2. Okay, so this is a homework due on the 30th. Okay, and again, same announcements as last class. Okay, these announcements, right? Doesn't continue the next page. It's right here. Okay, test 2 is on December 2nd in class on Zoom. The review for test 2 is on November 30th. Test 2 is on December 2nd in class on Zoom. Test 2 is on December 2nd in class on Zoom. The review for test 2 is on November 30th. Test 3 is on December 9th in class on Zoom. And the review for test 3 is on December 7th. Okay, so it's right there. Okay, so I will see you next class, and come with questions about test 2, because the review for test 2 is when I see you next on the 30th. Okay, bye.